All right, everybody. As promised, I wanted to run through the inclined plane problem, at least one of the inclined plane problems, maybe two. We'll see how much time I have. But to make sure that we go through at least one example before I turn you loose on some problem set. Now, this isn't going to be the only time we practice them, and we'll do some more in class on Monday and Tuesday. But I wanted to give you something to look back on in case you needed to look at it again or look at it a little more slowly or whatever it is. So, off of the problem set that I gave you today, it says forces on an inclined plane, components of gravity. We started off looking at number one. Number one says that a car rests on an, I'm trying to read it from across the room, sorry. A car rests on a slanted ramp leading onto a car transporter. The car's brakes and transmission are released, so only a cable attached to the car prevents it from rolling backwards off the ramp. So that part there indicates that we have no friction in this problem. It says the car has a mass of 1,000 kilograms, and the ramp is inclined at an angle of 15 degrees. If the car is motionless, find the tension in the cable and the normal force from the ramp acting on the car. So as we did in class, we have two unknowns in this problem. First is the tension in the cable that is acting on that car. In the picture, that relates to this cable right here that's holding the car onto the ramp. Okay. And then the next thing, so we'll handle all of that stuff in red. And then the next thing we're looking for is the normal force from the ramp acting on the car. So that's going to relate somewhere in this general area, right? Normal force being that support force that we've talked about before. Both of those unknowns. Things that we know. We know the mass of the car equals 1,000 kilograms, and we know that there is an angle. In this case, it's theta. It doesn't really matter what we call it, whether we call it theta or whether we call it alpha. It's just some way to indicate the angle. Is 15 degrees, and that's the angle of inclination between the ground and the ramp. All right, next step. I took the picture of the car out, okay, and let's save that for later. Even though you know what's going to happen, but still. So I took the picture of the car out so we can start working on a free body diagram for this problem. So the first thing we said that we can do is we can add the force of gravity into this whole mix. And that force of gravity is still equal to m times g, the mass of the object times the acceleration of gravity. But more importantly, maybe for this kind of problem, is the fact that gravity is always going to act straight downwards. Regardless of the fact that this object is now in an incline, the force of gravity still acts straight down. It's still equal to m times g, which means in this case, the force of gravity is equal to 9,810 newtons. Then, going back to the setup of the problem, we said that there were two forces that we're concerned about. First is the force of this cable that's holding the car in place, and the second one is the normal force from the ramp acting on the car. Let's take the cable first. That one's a little easier. So, if we take the cable is pulling. That's what cables do. So that cable is applying a force to the front of the car that looks something like that, along the direction of the force, or along the direction of the cable as shown in the picture. And then the last force is the normal force. Like we discussed in class, or if you weren't there, we'll discuss it now. The normal force, the way it gets its name is that normal is another way of describing perpendicular. So that force, the normal force, must be perpendicular to the object that is creating it. In this case, the ramp is creating it, right? That's what we said here, that's, oh, not what I wanted. The ramp is responsible for the normal force. But now in this problem, because the ramp has tilted, that normal force needs to be perpendicular to it. So I'm just going to do this for now, right? And it's going to be applying a force that looks something, let's go like that. Okay? Those are the three forces that are acting on the car. We already established before there was no friction. So those are my three forces. If we go back to the problem itself, we talked about that one key piece of information is the fact that the car is motionless. We said the lack of motion is one of our conditions that we can show equilibrium, or that's one of the conditions of equilibrium. And in two dimensions, we define equilibrium as no net force on the x-axis and no net force on the y-axis. These still have to be true, even though now we've inclined the surface, or we've put this object on a ramp. Those conditions still need to be met. So what I'm going to do here to show things maybe a little bit more clearly is I am going to take and I am going to get rid of, I'm not going to do that. I am going to get rid of the car. So now we're just left with the three forces that we were working with before. And I'm going to adjust those forces so that they all meet at one central location so we can draw ourselves a free body diagram. There's the three forces that are acting on the car. We talked before that we'll use the red to represent the tension force, and then we'll use the blue, to represent the normal force. Where do we go from here? Well, we can start this problem just like we've started every other problem so far in this chapter. I'm going to grab my x and y axis that I made previously, and I'm going to paste it onto this drawing, and I'm going to adjust it to this point right here, which is pretty much how we've done these problems in the past. Now, like we explained in class, if we did this problem the way that we've done it in the past, because the red tension force and the blue normal force are not on one of the two axes in this problem, the way we do this problem in the past is that we'd add a horizontal component for tension and add a vertical component for tension, and then we would add a horizontal component for normal force and a vertical component of normal force. We'd go about finding the sides of that triangle, and then, because we know that equilibrium still exists, right, where we have no net force on the x-axis and no net force on the y-axis, we would have to say that those two upward components would have to balance out the gravitational force, and then the two horizontal components would have to balance each other to give us that net force equal to 0. But as we discussed, there is a problem with that in this section, and that problem being we don't know what the normal force is, we don't know what the tension force is, and that makes finding components difficult if you don't have any side of the triangle. That's where the procedure for this problem deviates from what we've done before. So I'm going to get rid of these components. They're still there, or they still exist, at least in this frame of reference, but we can't really do anything with them. So here's where we said this problem becomes different than we've done in the past. The only requirement for our frame of reference in this problem, that being the x and y axis, the only requirement is that the x-axis and the y-axis are perpendicular to each other. That's the only thing that's required out of an x-axis and a y-axis. We've always drawn it this way before because that's how you're introduced to it in math class. But in order to serve our purposes a little bit better, we're going to do the following. I'm going to take my x and y axis, my frame of reference for this problem, and I am going to rotate them, in this case, a total of 15 degrees. By doing this, we find that two things happen. Well, actually, three things happen. First, the tension force now rests on the x-axis. The normal force now rests on the y-axis, and the gravitational force does not rest on either axis. By rotating the axis 15 degrees in this case, I have now made the x-axis parallel with the inclined plane of this problem, that being the ramp of the car carrier. I've now made the y-axis perpendicular to the ramp, or the inclined plane in this problem, which helps us out because now The red force, the tension force, and the blue force, the normal force, which were unknown before, which made component vectors difficult, now rest on the x-axis and the y-axis respectively. And that means they don't have components. We don't have to break up forces that are components or on axes into components now. Okay? But the one thing that changes now is the fact that gravity is no longer on either the y or the y-axis, which is where it usually ends up. But that doesn't change the fact that if a force is not on the x-axis or the y-axis of the problem, we still treat it exactly the same way. So in this case here, we're going to have to break up gravity into its components. So I'm going to get rid of this for a second, just because it's clouding up my picture. And I'm going to label this as 9810. Gravity does not lie on the x-axis or the y-axis, so that means it has components. And we talked about that the components have to lie along the x-axis and the y-axis of our problem. So if we're going to treat this problem like this, we're going to draw component vectors for gravity. One along the horizontal axis, one along the vertical axis, just like that. I'm going to make my horizontal one a little shorter. Okay? Just like that. Now, that doesn't help us a whole lot. But remember, we can move vectors around, so I'm going to take my horizontal vector and bring it down here. If we look at this angle right there, that's the angle that sits between the horizontal component and the vertical component of our gravitational force. If the horizontal component is along the x-axis and the vertical component is along the y-axis, that means that there has to be a right triangle right there, or a right angle right there. And that makes this a right triangle, which it should be. Here's the problem that people run into when doing this problem. They want to try and make the right triangle the wrong way. The gravity has to be the hypotenuse of the right triangle. It has to be. Whenever we're breaking up any other force into components, that force is the hypotenuse of the right triangle. So gravity has to be the hypotenuse of the right triangle. That's important. That means your triangle has to look something like it does up here on my board, okay, or on the screen. If you're having trouble seeing that, if you want to, you can move this stuff out of here and make it as a separate triangle. That's perfectly fine. If that's going to help you see it better, fine, go ahead, no problem. I don't got a problem with that. And then if you even want to, you can do this. You don't have to do this necessarily, but you can make it look like that if you want to. I don't care, as long as you figure out what the components are. Okay? Now, something that's important though. In order to find the components, you need to have a side of the triangle and one of the angles, so you can use your trig functions. If you restore this back this way, and I bring it up here, okay, rotate a little more so it fits right. On this green triangle, we only have a side. We know that there's a right angle, but that doesn't help us when we're doing trig functions. Here's the trick to doing the inclined plane problem. Back in the statement of the problem, it told you that there was a 15-degree angle between the ground and the ramp. Right? It was labeled as angle alpha in your picture. That's 15 degrees. I'm going to tell you something right now, and you can either take it on faith, or when you get back into class on Monday, you can ask me about it. The angle at which the ramp is inclined off the ground is always, always, always exactly the same angle as that angle right there. The pink dot on the screen. That pink dot angle is always the same angle, is equal to the angle at which the ramp is inclined off of the ground. So in the case of this problem, because the ramp was inclined 15 degrees, that makes this angle alpha 15 degrees as well. Armed with that information, you should now be able to find the two other sides of that triangle. So do so now. Just because the triangle is slanted doesn't change the relationships between the sides and the angles. So figure out the two sides, the two remaining sides. And that's what I get when I do my sine and cosine and get the two sides of the triangle. Now, back to our business. Going back to what we were actually doing. Here, we know that there still has to be equilibrium in this problem because the object is not moving. It says that the car is motionless. And that means we have to balance on the x-axis and the y-axis. By tilting the x-axis and the y-axis of this problem like we did, that should become a little more clear. If you look at the horizontal axis in this problem, right, this one right here, there are only two forces that exist along that horizontal axis. There is the horizontal component of gravity and the tension force. If there are only two forces acting along that x-axis, and we know that the net force on the x-axis has to be 0, that means that the tension force in this case has to be equal to 2,539 newtons, give or take some sig days. On the other hand, on the y-axis, this one right here, right, there are still only two forces. There's this vertical component of the gravity, and then the normal force. If we have to have 0 net force along the y-axis, that means that the normal force has to be equal to 9,475.7 newtons. Once again, give or take some sig days. By tilting the x-axis and the y-axis in this problem, what we've done is that we've taken those two unknown forces that we couldn't figure out and break into components before and made them along the x-axis and the y-axis so that now we don't have to break them up into components. That requires that we break gravity up into components, which we haven't done before, but it's no different than how we did it before. It's just a different force that we're breaking up into components. So that's one example. We'll see how time goes. I might post you another example. This problem is very similar to, if I remember right, I believe number 2 is also very similar to this problem, and I'll show you problem number 3 or later, but I'll try and post you another video.